Now it's time to take a look at different cases of linear momentum. So we could call this all our cases. All our cases can be broken down into two different types that matter. We have explosions. And we have collisions. Things flying apart and things smashing together. When it comes to collisions, there are two types. We have the type where kinetic energy remains constant. And we have the type where kinetic energy decreases. There's a special name for each of these. When it remains constant, it is called elastic. When it decreases, it's called inelastic. Some words we might associate with elastic are bouncy, whereas inelastic is sticky. Some other attributes is that when it's elastic, the interactions are short-term. And for sticky, the interactions are generally longer-term. For elastic, there's usually no deformation of the bodies because they are hard, rigid, like billiard balls, excuse me. Bowling balls could be hard too, but billiard balls are much harder. Steel bearings. Well, with sticky interactions, there is deformation. We have flexing, squishing, compressing. These tend to be soft, like balls, or anything that can crumple. So when it comes to interactions with conservation of linear momentum, we've got all our interactions. Some of them are explosions and some of them are collisions. That's the first thing we want to ask ourselves. Is this an explosion or is it a collision? Whenever we have particles interacting with each other or changing their motion, we think momentum first. Once we've established it's a collision, we ask ourselves, is it bouncy or is it sticky? Are the objects short-term interactions? Are the bodies hard with no deformation? Or they tend to be soft, flexible, longer terms of interaction or squishy in some way? And when it's bouncy, it tends to be an elastic collision. And if it's sticky, it's inelastic. But what I'll tell you right off the bat is this is a false distinction that I'm not sure is even useful, to be honest with you. If there's utility in it, it's a way of getting us to figure, is it more like this, where the kinetic energy remains constant, or is it more like this, that it decreases? Because it turns out there is no such thing as an elastic collision. There is no such thing as a perfectly inelastic collision. How we get at this is we ask ourselves to compute a ratio of the initial kinetic energy and the final kinetic energy. If the kinetic energy at the end is equal to the kinetic energy in the beginning, then that ratio is 1. And we call that a perfectly elastic collision. It is ideal. It means that no kinetic energy was converted into thermal energy or vibrational energy or gravitational potential energy or any other kind of interaction. It is ideal, which means it never happens. That being said, we have things like ideal gases, where the assumption is every time a gas molecule hits another one, it's a perfectly elastic collision. No energy goes into changing to deforming it or interacting with it or converting energy into anything at all. They're just super hard. The interactions are super fast. There's no transformation of one type of energy to another. So that's ideal. So we will never get a situation where the kinetic energy afterward equals the kinetic energy before, unless it's an ideal made-up problem or situation. Well, similarly, to get a ratio of 0 would mean that there would be no kinetic energy afterward. No kinetic energy afterward. Let's imagine that. We have this object that has a velocity equal to 0. We've got some other object that comes in and collides with it. Is it possible for this object to have a 0 velocity afterward? Excuse me, the system to have a 0 velocity afterward. Can this first ball 1 hit ball number 2 and both of them come to a complete stop? The answer is no. But it is more and more likely as the mass of this one increases. As this gets larger and larger and larger and larger, and this is smaller and smaller and smaller, it will have less and less of an effect on it. So we also, the point is, really never have that either. All there is are shades of gray in between, where we determine how much kinetic energy is left over. 100% doesn't happen. 0% doesn't happen. And the other reason we know 0 doesn't happen is because momentum must be conserved. That's always true. So if something is moving beforehand, something must be moving afterward. For the momentum afterward to be 0, the momentum beforehand must have been 0. And if the momentum was 0, the kinetic energy would be 0. So we cannot have the two extremes, which is what's represented by calling something elastic or inelastic. They are extremes, and what we want to find out is the elastic nature of the interaction, which is represented by this ratio of the final kinetic energy to the initial kinetic energy.